Bismillahirrahmanirrahim. Hello, dear guys. I am Professor Azmat Ali, and you are watching my channel Higher Mathematics. I welcome you all in class of complex analysis. In today's lecture, we will discuss about harmonic function. So, harmonic function can be defined as a real valued function u or v is called harmonic or potential function. The other name of harmonic function is potential function. If second order partial derivative exists of u and u satisfies the Laplace equation, that is also called potential equation, which is gradient square u equal to partial square u over partial x square plus partial square u over partial y square equal to 0. So this is the simpler definition of a harmonic function. Harmonic function is always a real valued function. This is not a complex valued function. So every real valued function that satisfied Laplace equation whose second order partial derivative exists is called harmonic or potential function. Next here there are some important facts about Laplace equation. As this is a Laplace equation and this is a second order partial differential equation, so every solution of this equation is called harmonic function or potential function. Thus u is a harmonic function. As Vx y is an imaginary part of the analytic function f of z is equal to u plus iota v. As you know, throughout my lecture, I have set f of z as an analytic function whose real part is u and imaginary part was v. So that's why I think necessary to clear that if v is imaginary part of analytic function, then as to similar to u, here vx y, that is the imaginary part, also satisfy the Laplace equation. Thus it is also a harmonic function. As u and v both are itself real valued functions. Here v is the imaginary part of the function f of z, but it doesn't mean that v is imaginary function. V is a real valued function and u is also real valued function. So before going to discuss the example of harmonic function, I want to discuss about the determination of conjugate function. Let f of z is equal to u plus iota v is an analytic function. For real valued function u, we can determine its conjugate function, that is called here vxy. So next I am going to discuss some examples. How in these example I will show how we can prove the real valued function is a harmonic function and how can we find conjugate function of the given real valued function. So I am going to write prove that u given by the following is a harmonic. Obtain its corresponding conjugate and the original function f of z, that is the analytic function. Here there are the three examples. In the first part of the example, our u is e raised to power x cos y. Second is x cube minus 3x into y square, and the third one is e raised to power x into x cos y minus y sin y. In all of these examples, we need to show that here u, that is the real valued function, is a harmonic function, and corresponding to this function we are required to find its conjugate function, and finally we need to find the original function, that will be analytic function f of z. So let us start from the first part. In the first part, u is e raised to power x cos y. U is called harmonic function if it satisfies Laplace equation, that is the gradient square u is equal to partial square u over partial x square plus partial square u over partial y square equal to 0. So firstly we will find partial u over partial x, which is equal to partial over partial x. The value of u is e raised to power x cos y. As you know that uh, when we take partial derivative of the given function with respect to x, then y will be constant. So here cos y is considered as constant coefficient, and applying the partial derivative on e raised to power x, as partial derivative of e raised to power x is e raised to power x, so partial u over partial x will become e raised to power x into cos y, that I am going to write equal to u, because you know that here u is equal to e raised to power x cos y. By taking again derivative on both sides with respect to x, this term will become partial square u over partial x square, and this will become partial u over partial x. But as here partial u over partial x is cos y into e raised to power x, this shows that the second derivative of u with respect to x is also e raised to power x cos y. Next we will find partial derivative of u with respect to y here. Now in this case x will be considered as constant, so the term e raised to power x will be considered as here constant coefficient. So applying partial derivative on the term cos y, derivative of cos y you know that minus sin y, this will become partial u over partial y equal to minus e raised to power x sin y. By applying again derivative with respect to y, we have partial square u over partial y square equal to, as the derivative of sin y is cos y, so this will become minus e raised to power x cos y. Next you can observe that here the value of partial square u over partial x square plus partial square u over partial y square equal to 0, because here partial square u over partial x square is positive e raised to power x cos y. On the other hand, the second derivative of u with respect to y square is minus e raised to power x cos y. So both will be cancelled, and answer is equal to 0. This shows that u is a harmonic function. So we have shown that u is a harmonic function. Next we find its conjugate function, that is here represented by vxy. By using the CR equation, that is the Cauchy-Riemann equations, you know that partial u over partial x equal to partial v over partial y. This is the first CR equation. As here we have no information about partial v over partial y, because we are going to find v, but here partial u over partial x is equal to e raised to power cos y. This implies that partial v over partial y equal to e raised to power x cos y. By taking a integration, by integrating partially on both sides with respect to y, as similar to partial derivative, here when we integrate partially with respect to y, the term of e raised to power x will be considered as constant. So by taking this as a constant coefficient and taking outside from the integral sign, and on the left side of the integral this will become partial v over partial y into partial y. Partial y will be cancelled here, and as you know that integral and partials are the inverse operator here, this will become v integral sign of integration of cos y is sin y plus constant of integration. Here one of the important thing that is here, as you know that when you integrate function, then we take constant of integration c, because here we are integrating with respect to y partially, so in this case x will be considered as a constant. So gx is also a constant function here. Since we are integrating partially with respect to y, so x will be constant, so here constant of integration will be a function of x, that is gx here. So we will write here gx, not constant c firstly. Saying this as a question number 1, our next target is to find gx. For this we will take derivative on both sides, and then we will use the second CR equation. So taking derivative of 1 with respect to x, we have partial v over partial x e raised to power x into sin y. You know that sin y is a constant, and derivative of partial derivative of e raised to power x is e raised to power x, and derivative of gx is g dash x here. This is equation number 2. By using CR equation, that is the second CR equation is partial v over partial x is equal to minus time partial u over partial y. As the value of partial u over partial y was minus e raised to power x sin y. So by putting here a value of partial u over partial y, this will become partial v over partial x is equal to e raised to power x sin y. This is question number 3. By equating 2 and 3, or by putting the value of partial v over partial x, that is e raised to power x sin y, in question number 2, question number 2 will become, here the left side will be left side is e raised to power x sin y. This term will be cancelled, and the remaining we have g dash x equal to 0. By taking integral on both sides with respect to x here, now at this time we take simple integral on both sides, not a partial integration. As the integral of g dash x is simply gx, and integration of 0 is a constant, that is represented here c dash. So by putting the value of c dash in question number 1, our corresponding conjugate function v is e raised to power x sin y plus c dash. So conjugate function of u, that is e raised to power x cos y, is v, which is equal to e raised to power x sin y plus c dash. Next and the last thing, we have to find original function f of z. Next original function f of z is f of z, which is equal to u plus iota v. Here u is e raised to power x cos y plus iota, and the value of v is e raised to power x sin y plus c dash. By multiplying with iota inside the brackets, we have f z is equal to e raised to power x cos y plus iota e raised to power x sin y plus iota c dash. Let iota c dash is equal to c, because c dash is a constant of integration and iota c is imaginary number, pure imaginary number, say this equal to c. So this will become, and by taking e raised to power x as a common here, this will become e raised to power x cos y plus iota sin y plus c. By using the Euler identity, you know that e raised to power iota theta equal to cos theta plus iota sin theta. By this identity, this will become e raised to power iota y plus constant c. Because base is same here, power will be added here. This will become e raised to power x plus iota y plus c. As you know, x plus iota y is here equal to z plus c. So our original function, that is the analytic function here, f of z is equal to e raised to power z plus c. In the similar manner, I hope that you can do next 2 problems here. I hope today lecture will be beneficial for you. If you think this video was helpful for you, kindly like, share and subscribe my channel. Okay, goodbye.